it's a topic is Steinitz theorem, and those who missed last week's talk, I tell them what it is. But first, I want to let everybody know that tomorrow at 11:30 we have a guided tour at the Arithmeum. Arithmeum is a mathematical museum, not far from here. And part of a building is also nice, and it's part of the operations discrete mathematics research group as well.
So we meet there at 11:30?
We meet there at 11:30, and the guided tour lasts till 1 o'clock. And the entrance fee was waived because we are colleagues. This is my little victory. So, Steinitz theorem from 1913 says the following. Steinitz. V is a subset of the unit ball of a unit ball in RD. Unit ball. This is finite. And there is one more condition, the sum of the vectors in V is 0. So this is a set of vectors, and you start from the origin and it zigzags out and comes back. And then it says that there is an ordering. V equals V1, Vn, such that the maximum over all k of sum 1 to k vi, partial sums along this ordering are all smaller than a constant that only depends on dimension, does not depend on the vector set here. And the result I proved last time was that it is always smaller than or equal to d, which is an excellent result, very strong result. I gave you a wrong proof of the same thing for the Euclidean norm, and that was a nice proof as well, but it gave 2 to the d basically. So this is much better. And the best constant that you can write here is a certain number S of B, which is the Steinitz constant of the norm, or the unit ball. And the theorem I proved last time is that it is smaller than or equal to dimension. And it's a beautiful proof, but it does not see the norm at all. The norm comes to play in the proof in the last moment, and you only use it that alpha times x norm is smaller than alpha absolute value times x norm. And you cannot use that it is Euclidean or maximum or L1 norm, etc. The question was motivated or was by another question of Riemann that says that he proved that a conditional convergent series of real numbers can be made to converge to either nothing or a single point or every point in the line by a suitable rearrangement. And Hilbert's question was, what is the case in higher dimensions? If you take a conditionally convergent series of vectors, what are the set of points that it can be made to converge to? And the answer is, using this theorem, this is the key step in that proof, is that it is an affine subspace. So either a single point or the empty set or a line or a space or a plane, etc. I gave you several applications. One of them, I did not explain this application, the Hilbert's question, the positive answer to Riemann's question, but I gave you an example in scheduling, right? Mm-hmm. I gave you another example in
Balancing vectors.
Pardon?
Balancing. The balancing vectors.
Yeah. And I want to give you another application, which is, there are several applications. And here is another application which is due to...
Can I ask,
you need more of what? Of this norm that you need more of a norm.
Some norm.
Some norm, which is written here. So this is typically a central symmetric convex body containing the origin in its interior, but for this proof you don't have to, does not have to be centrally symmetric. So there, I want to give you another application, but first I want to mention a similar result. So you have the same system, finite, no, not the same system. Vectors, set of vectors in -1, 1 to the d, and you know that finite, and the sum of the vectors in V is 0. So same condition, but for this norm. And what you want to have is an ordering, find an ordering V1, Vn, such that sum from 1 to k Vi, jth component of this vector is smaller than a function that only depends on j. So this is an infinite version of the previous theorem, because it tells you that if it's true that you can, no matter what you have, what dimension, you can find an ordering so that the first component is less than 10, the second component is less than 10 squared, the third component is less than 10 to the 3, etc. So just I give you an example for f of g. And so this was a question, and of course it has some implications for the conditional convergence series as well, which I don't explain in detail. I proved this one with a very big bound here, long ago, with about 2 to the 3 to the j. And I won't tell you that proof, but I tell you that there was a much stronger proof by Joseph Beck, which shows that this can be made less than j to the 4 plus epsilon for any epsilon, and here is a universal constant. So this is a much stronger result. This is Joseph Beck. And his proof is long and highly non-trivial, and I won't be able to explain anything about it, but the basic idea later. And so another application is this one. You have a set of vectors in -1, 1 to the d, and finite, and the sum of the vectors in V is again in -1, 1 to the d. And the size of the set, say V equals n. This is a theorem by Matuszek, Buchin, Palberg, and someone else whose name I don't. And it said that then there is a subset. No, and n is larger than 4 times 2d to the d. So n is large enough. Then there is a subset U of V, proper subset, at least 2 elements, such that the sum of the vectors in U also lies in -1, 1 to d. So if a certain set of vectors in this box sum to a vector in this box as well, then there is a non-trivial subset of this set V that also sum the elements of which sum to in this box as well. So this was needed for some computer science problem, but I don't want to go into the details. I can tell you essence of the proof of this application.
So the cardinality of U is bigger than what?
If 4 times 2 to the 2d to the d.
This is V, but U.
U is larger than 2, because one element satisfies this property automatically, right? So that's why I insist on this being larger than 2. Right? Because it says that every vector here lies in this box. And I want to have a subset whose sum lies also in this box, other than the one element set and the full set. And I tell you what the proof is.
So it may happen that that the cardinality of U has to be really bigger than 2.
Yeah. You can't guarantee that.
That just for 2 it's
Yeah. So the proof is that.
Let me ask about here. So you say that this is wrong proof. So bound that the road is not correct.
long.
Long.
What was the question?
No, I heard that it's a wrong proof.
You are interested in this proof?
Not interesting. I'm interested in what you're saying.
I also understood the proof is wrong, you said, but
You said long.
you said no.
It's a correct proof. It's a long and complicated proof with a construction which guarantees a certain family of subsets with 7 properties. And I don't have time for that today. So the proof goes this way. The sum of these vectors is a vector that I call minus V naught, if you wish. Then the sum of the vectors in V plus V naught is 0. Right? So by Steinitz theorem, I can order them so that every partial sum is small within the ball of radius of D. So every partial sum of that guy is in the box D minus D to the D. Right? And I may assume that V naught is on the upper half of this sequence. So I have V1, V2, etc., Vn, the last one, and V naught is somewhere later than the middle. Because it doesn't, if I change the order, the same remains true. So if I go the opposite order. And now I choose this as the first partial sum, this as the second partial sum, this as the third partial sum, this is S naught, this is S2, this is S4, etc. The last one is going to be S almost n half. Are you with me? They all lie in the D by D box. If there are enough many of them, then 2 of them lie in the same box. Are you with me? So far so good. So the difference is that at least 2 element set, which has some in this box here. In this box. So this is a fairly direct application of Steinitz theorem, but you see how useful it is. You just take it out from the black box and apply it, and you get it. So a related topic is balancing vectors. And this is my next topic. And I gave you an example last time, which is a game. And the game consists of a pusher and a chooser. And it is being played on the plane. And the pusher offers a unit vector in Euclidean norm on every step. So pusher and chooser offers a vector Vn in step n, and the chooser chooses an epsilon n, a unit vector in the plane, and this chooses an f plus or minus 1. And after n steps, the position is some 1 to n epsilon k vk. So this is a vector in the plane. And pusher wants this vector to be as big as possible. Wants to push away from the origin, this position. And chooser wants to keep it close to the origin. And then it's a very simple game, because at every moment, pusher chooses a vector orthogonal to the present position. Right? Then the length is, the square of the length is increased by at least 1, no matter what choice chooser makes. And chooser always chooses the two vectors for which the distance from the origin is smaller. So that means that the value of the game is square root of n exactly. Right? So this is a very simple game, because the pusher can reach that the square of the distance increases by 1 at least, and the chooser can reach that the increase in the square is at most 1 at each step. And the variant I offered is the following. Instead of offering the whole unit ball, pusher can only offer these vectors here. These vectors. Of course, then it can offer these vectors as well, because offering v and minus v is just the same thing. Right? So what is the value of the game in that case? And I have some partial result that in that case the value of the game is larger than square root of 2 minus 1 times square root of n. So the value is smaller than, and I don't have anything better than square root of n. So not even 0.99 square root of n. So this is a question that I could not solve. And any successes in a week? No. What a pity. Yeah. So this is just a sidekick, and the balancing vector question goes this way. V is a sequence of vectors this time. V1, V2, etc. Vn can be actually infinite, doesn't matter. That all lie in the unit ball V of Rd. And find epsilon 1, etc., epsilon 2 in minus 1, 1, minus 1, 1, so that the sum of epsilon I vi from 1 to k maximum is smaller than a constant that, similar to this one, does not depend on anything but the norm. Right? So this question was around for quite some time. Dvoretsky considered it in the plane in 1963, and in 1981 I proved that together with Greenberg that this is always smaller than 2d minus 1. So then there exists, and this is a theorem, and it's Greenberg and myself. And I want to give you the proof of this theorem. Okay. So what I'm going to do is alpha k is going to be a mapping from V1, Vk plus d to 0, no, to minus 1, 1, this interval. So this is a coefficient, a real number between minus 1 and 1 associated with every vector here, right? So that it is a linear dependence. That means that sum alpha k v sub I equals 1 to k plus d is equal to 0. And I want to make sure that very few of the alpha k are different from plus and minus 1. I want to make sure that very few of the coefficients here are different from minus 1 and 1. So more precisely, a number of I such that alpha k vi is larger than minus 1 and smaller than plus 1 is at most d. This is my main requirement, but I also need one more thing, that if alpha k of vi is equal to 1 or minus 1, then alpha k plus 1 vi is equal to alpha vk alpha vi. Sorry, alpha. So if somebody reaches 1 or minus 1, it remains minus 1 or 1. No change in that one, from that onwards. So is this clear? I make a picture of this one as well. So this is alpha k is, and here I say that this is on the vectors v1, vk plus d, but I could say it depends on 1, 2, 3, and k plus d. And then the picture is this one. Here is 1, 2, 3, etc., k plus d, and the other numbers. Here is plus 1, here is minus 1. This is plus 1, this is minus 1. And my function looks like that. Color choke. So there are several values that it is 1. And then several values that it is minus 1. And then again, several values that it is plus 1. And then there are at most d that are between. Right? This is what I want to achieve. And these, I call them floating variables. The floating variable, the number is at most d. And how shall we do it? So let me say alpha 1 should be a linear dependence of the first d plus 1 vectors. Right? There are d plus 1 vectors, there is a linear dependence. I multiply it by a factor so that the maximum absolute value coefficient is 1. Right? Then I kick out one value to here, and there are at most d floating variables. Right? Now assume that we are in this position. Alpha k is constructed. So alpha 1 is done. Now I step k to k plus 1 comes. And then I have an alpha k linear dependence here satisfying everything. And I choose k plus d plus 1 with 0 level. I have another linear dependence. The coefficients are all same as in alpha k, but this vector comes with coefficient 0. I have d plus 1, at most d plus 1 floating variables. They have a linear dependence. I add this linear dependence to my present linear dependence so that one guy is kicked out to plus or minus 1. Is this clear? So I get a new picture here. Somebody is kicked out to negative 1, and then I get another floating variable here, at most d. And I kept every 0 and every plus and minus 1 the same, because they did not touch them. Right? So this is almost the end of the proof. What happens is that alpha k stabilizes. More and more alpha k's are alpha vi stabilizes. It becomes plus or minus 1 and remains plus or minus 1. And so in the end, I will choose epsilon vi equals alpha k vi if it is 1 or negative 1 once. So then epsilon is defined for every vector here except at almost d. And for those one, I choose whatever I want. I don't care. Okay? And then let's check what happens with this sum here. So let me write it out. Sum from 1 to k plus d epsilon I vi. I may assume that if k is smaller than, if I take only epsilon times vi, and if I take only, I wrote here k plus d, but if the upper index is smaller than d, then we are done. Because the number of vectors is at most d, and no matter what vectors I choose, the sum is smaller than d. So in this case, I consider, I can take away from this one 1 to k plus d alpha k vi. So this is nothing else but epsilon I minus alpha k vi times v sub I. Now this number here is 0 except at most d places. Right? This number is 0 except for at most d places, and then I have d summands, each has value 1 here and at most 2 here. So then I get that this is smaller than or equal to 2d. I promise 2d minus 1, and I leave it to you to check how to reach that one. Now this is let me write here S of B as the sign sequence constant of the norm B, the smallest number that you can write over here. The smallest number that you can write over here. And this proof tells you that this number here is always smaller than or equal to 2d minus 1. So, yeah, so, are you happy so far? Can we go on? Sure. So there are variants to this question. So here what you are given is on step I, choice between vi and minus vi, right? The vector and its opposite. What happens if I give instead a set of vectors here, and a set of vectors here, and a set of vectors here, you at most unit vectors, and you have to choose one from each so that these partial sums are small. Well, if this, let me call this subset instead v sub 1, v sub 2. If v sub I don't contain the origin in the convex hull, then say all of them can be separated from the origin by a line. Then you just push it out to infinity quickly. So the natural assumption is that the convex hull of each vi contains the origin, just like in the plus minus v case. Right? So what happens if you are given a sequence of subsets of the unit ball with the convex hull containing the origin? Can you pick one element from each so that this sum is small? And essentially, the almost identical proof works in that case. It uses linear algebra only. So this is one variant of that, which I don't go into details about. And another one is so what you want to do in this original setting is you want to split the set V into two sets, the set V plus and the set V minus, so that the V plus is where epsilon is +1, and the V minus is where epsilon I is -1. And then you want to see that if you go up to level k in each set, then the sum of the first one up to k and the sum of the second up to k is close to each other. And you can check that it means that so the sum of the vectors in the first of V plus set up to k minus the sum of the V plus up to k is in the mole of radius 2 V times V, right? This is what this inequality says. Right? Are you with me?
Yeah.
This is an unusual notation. This means that I add the vectors in this set up to index k, and I add the vectors in this set, this is minus up to k. And of course, the sum of the k's up in V plus and plus this one, sum of the vectors in V minus is equal to the sum of the vectors in V up to k. So if you add these two together and then this cancels, and you see that this sum here is in the half of the sum up to V, up to k, plus d times b. So it tells you that this sum is in sum sum V in up to k, 1/2 plus d times b. And the same applies to V minus, V plus V minus. And then there is a question. Can you split it into 5 parts? So that each part, this sum up to k, is close to the 1/5 times this sum. So this is not plus. Yeah, this one is in yeah. Are you with me? Shall I repeat?
No.
Okay?
That's okay.
So the question is whether this can be done. And the answer is yes, you can do it. And you can split it into R sets so that each partial sum of any set is in the mole of 1/r times this sum plus 2.5 times d times b. Right? So this you can yeah. So this is another result that I have no time to prove, but this is a yeah. More interesting is the next theorem, one of my favorites in this topic, which is hogy Csogányán transference theorem. This says the following. For a symmetric norm, or a symmetric norm, S of B is smaller than or equal to S of B. So this makes a connection between the Steinitz problem and the sign sequence problem. Right? So this is a
Symmetric, what do you mean by symmetric?
pardon me?
By symmetric, what do you mean?
Unit ball.
The unit ball is symmetric.
Central symmetric.
Central symmetric. This theorem holds for non-symmetric balls as well, but that one does not. So this is a very powerful and interesting theorem, and actually, Jorgenbeck's proof of this result is based on a balancing vector result, which tells you that given a sequence of vectors in plus or minus, yeah, in the maximum norm, then there are signs so that the jth component of every partial sum is smaller than j to the 4 plus epsilon. Instead of giving you Chobanian's beautiful proof, I tell you how Joseph Beck's proof proceeds for this one with the signs there. And he starts with, so here he proves it first that every coordinate is +1, -1, or 0. Right, a very special case. And so here is a big matrix, infinite if you wish. And here are, in the cells, there are zeros, +1s, -1s, etc. And you want to give a sign to every column so that the partial sums are small. And the following is the starting idea. If I see a 0 here, I don't care what sign it has, I just fix it. If I have a 1 here and a -1 here, or a 1 and a 1, then to this one I will give sign +1, and to this one I will sign -1. And then I glue together this column completely. And then in the new matrix, this is going to be a 0. Right? And here I get numbers which are not too big. So each time I either glue together two columns, or just leave the columns alone, and what I have here is 0, 0, 0, 0, 0. Right? And now, this is a new vector. This is a new vector, slightly larger than my original vector, but I can give you any sign I want later, because this will just flip the signs, original signs here. So this is easy, but once in the second step I have these two vectors here, and I know that the coefficients are -2, -1, 0, 1, 2, and you fix that if you have 21 of them, then you can find 5 among them that sum to 0 with suitable +/-1s. So if out of every 21, you can find 5 that gives you a 0 value in both places. And those 5 will be glued together with a 0 coefficient. And then, so out of the 21, use that 5, and then you add 5 more, and find another 5 that sums to 0, and fix so this is going to be another block here, 5 block, and later another 5 block. But no matter how far you go, as this is 0, this is 0, this is, it doesn't matter what sign I get later. And only the sum of these ones matters, but there are less than 21 of them at each stage. Right? So then, after this one, these two columns are fixed. And then I have another set of larger vectors, and I know that all of them are bounded, right? Bounded components. And then this is a pigeonhole principle that you find a 0 sum, because so this is his proof for the +/-1, 0 vectors. And then there is another idea, highly non-trivial, that carries over to anything. So this is how you get to this quantity here, and Chobanian's transference theorem. I want to mention about Chobanian's transference theorem that I think it was 1983 or 4 that I was delegated to Tbilisi from my institute in Budapest to the Med Institute in Tbilisi, Georgia, in the Caucasus Mountains.
He's a probabilist, right?
Pardon me?
He's a probabilist.
Yes, he's a probabilist. A probabilist of Armenian origin, living in the Georgian capital, but the Georgian capital has a large Armenian population. And once you go there, you don't expect anything to happen. I mean, I'm introduced to the director of the institute, shake hands with everybody, and then give a talk and go back home. But Chobanya was different. He was interested in sign sequences. and we talked about sign sequences, and I keep still in touch with him. So that's a good thing. I mean, it's a good thing that a mathematician goes anywhere and can find somebody who he can talk to easy and meaningfully. Anyway, so this is Chobanya. Since then, he moved to he had a job in the States, and now he's back in Georgia. Yeah, anyway, so I promised you a matrix version of Steinitz, and that will happen on the So this time, matrix version. A is a K by N matrix, and Aij is an element of a unit ball, so in Rd. So this is a matrix whose entries are vectors, not numbers. And each entry is in the unit ball of some norm. And the assumption is again that the sum of the entries is 0. The total sum of the entries is 0. And we are interested in this quantity sigma m of A is equal to, so here is my matrix. This is, it has k rows and n columns, and this is m. And the sum of the vectors in this block is sigma m. So this is equal to sum k, j equals I equals 1 to k, and j equals 1 to m a I j. This is the sum of the first m columns, right? And you want this one to be small. In order to make this one small for every m, you have to have sigma n small, right? If sigma n, the total sum, is big, then you can't make everybody small. So we assume that sigma n of A is 0, and sigma, and C is a row permuted copy of A if this is the ith row, and in the ith row I can rearrange the vectors any way I like, right? Independently of, and in every row I can choose another ordering. So the sum of these k times n vectors is 0, and there is a good ordering according to Steinitz theorem that all partial sums along that ordering are small, but here I restrict the possibilities of rearrangement. I can rearrange the vectors only row-wise. So that's why I call it row permuted copy of A. And the theorem, and that is a theorem by Oertel, Paat, and Weismantel have the reason, saying that under these conditions there is a row permuted copy of A, row permuted copy C of A with sigma m A equal C norm max m smaller than a number that only depends on dimension, and this is 40 times d to the 5. So this is the result. It's interesting because it does not depend on the size of the matrix, only the dimension of the space, right? And there is another condition that is trivial because you can do it different ways, but you see the columns of this matrix are unit vectors in B times B product. And the sum of the columns is 0, right? So you can rearrange them by Steinitz theorem so that every partial sum is smaller than dimension of the space, which is k times d. So this is always smaller than k times d. So whichever is better is a bound. Yeah, and
So what's the name? I'm sorry. What
this is, I can write it out. It's Oertel, Paat, and Weismantel. And the paper appeared in the Met Programming, maybe
P-double-A?
Weismantel.
No, that is
P-A-A-T and O-E-R-T-E-L. Here is a new result of mine saying that theorem that this can be made smaller than 4d times d minus 2. So this is an improvement over this part. Over this part I don't have an improvement. So this is what I want to explain. Okay? And actually it is we will see that it is a stronger theorem in a certain sense, but something comes first before that. D is, so let me, for these conditions together form a set of matrices. This is A, K, D, K, N, and B. It's a set of matrices, K by N matrices, each entry equals an element of the unit ball and the sum is 0. Okay? So if D is in, and I drop K and B is in A, actually in this case you don't have to have it 0 sum, and epsilon is a epsilon ij, K by N matrix of plus and minus ones, then D of epsilon is epsilon ij, aij matrix. This is again a matrix in A. Again, I don't know if the sum is 0, but doesn't matter. Okay? And then there is a fairly trivial lemma. There is always an epsilon matrix with sigma m epsilon, d epsilon smaller than 2d minus 1 for every m. So this is a very simple lemma, and you will see in a moment, that I can list the vectors in this order. I go up and come back here, and then go up and come down here, then go up and come down here. It's an ordering of the vectors of D, right? Then there is according to that theorem, there is a choice of the epsilons, so that every sum is smaller than 2D minus 1. And of course, every block here is such a sum. So this is actually even more is up to this level it is smaller than 2D minus 1, but I only use it this way. And then the theorem is that S of the matrix version, this is the best constant that you can write over here, is smaller than twice SS matrix B. So here's another transference theorem. It says that the matrix constant, the Steinitz constant of a matrix, is smaller than twice the sign sequence constants of a matrix of the same norm.
B now centrally symmetric.
Pardon
B is now centrally symmetric again.
Yes. I will not have time to finish this proof, but I try my best. So for the proof, you choose a matrix A in A which reaches this constant here, right? Which means that, and I assume that this matrix A is in this form A1, A11, A12, A13, etc. Okay? So that means that sigma MA, the maximum of sigma MA norm is equal to S of B, and for any row permuted copy of A, C of A, sigma M of C is larger than S of B for some M, right? So this is the best one that reaches this level. It means that this is equal to SB, but no matter how I rearrange the rows of the matrix, I get a partial sum which is larger than S of B. Right? And then, so here is my matrix. And assume that n is even, n is equal to 2p, and then I create a new matrix D, which is equal to 1/2 times A, as it is I, this is 2j minus 1, minus A I 2j. So what happens is that in this matrix, I choose, this is the ith row, and this is this element, the next element, and I take this one minus this one as a new element. So this is a matrix in the set A, but this time A times n/2. And in the same B, because in the same B, right? Because the average of two unit vectors is a unit vector. And then for this one, there is a d of epsilon. There is an epsilon matrix such that sigma m of d epsilon is smaller than 2d minus 1. No, smaller than SSB of matrices for every n. Right? So this is what we have. And now I create a new row-permuted copy of C. So instead of writing out this whole matrix, I only write out the ith row, which is A1, AI2, AI1, AI2, AI3, AI4, etc., AIN, AIN minus 1. And then there will be a new matrix here instead of reorganized matrix. And what happens is that these two vectors go to this spot and this spot. And these two vectors here go to either this spot or that spot, etc. And the rule is that if so, for this difference, I have an epsilon, and if it is positive, this goes here and that goes over there. If this is negative, then this goes over there, this comes over here. Right? And the same applies to everybody here. I bet I will lose the ODS very soon. So this way I get a new matrix. And after some manipulations, you understand that this matrix satisfies S of B for some. So there are some inequalities that come into play that I prove it. Actually, this is Chobanian's idea, original idea, but in his case it was different. He did not have to create a new matrix out of it. But I better stop here because I'm afraid losing all of you soon.
You won't.
I will not.
You will not.
Because you stay patiently. Shall I?
Sure.
Shall I? So what happens is that I get a sequence here, and so if this one was positive, then this goes the first, this becomes the first element, and this becomes the last element. Which if I open up this epsilon here, then this goes with positive sign, and this goes with negative sign from over there. So this goes negative sign over there. Same applies here. If epsilon was negative, but this would go to the end, and this would come here. So what happens is that in this sequence, the ones that come with positive coefficient go to the first half, and in this order, and one comes with negative sign comes in this order. Now, if you want to compute the partial sum up to this point, right, then what you end up is, I have to write it on C I j is equal to 1/2 times A I 2j minus 1 plus AI 2j plus epsilon ij times AI 2j minus 1 minus AI 2j.
So this is how the rule applies where J is up to here. If epsilon is positive, then this one cancels and you get AI, this one, exactly. If epsilon is negative, then this cancels and you get this vector here, right? And so if you enter theCij's for fixed I and J equals 1 to K, no, for fixed J 1 to M, then here you get so in this case epsilon is positive, so you get these two, sorry. If you sum all of these, then you get sum AI J equals 1 to 2M. Sorry, this is 1/2 times, right? If I sum all of these, I get the first two M elements of the vectors. And in this second half, I get, this is Dij, so I get the sum of the Dij's up to M. So this is sum Dij epsilon Ij, and this is what you have to sum. And now you sum everything from A equals 1 to, I equals 1 to K, and sum I to K. And then what you have here is a 1/2 times sigma 2M of A. Are you with me?
So the Dij's are these.
Dij is this difference. And times this one is written here. So here you get the sums that I'm interested in. And here I get the sigma M the epsilon. And this one, the 2 is disappeared because this is divided by 2 is Dij. Right? So this is sigma M of C, and this is in the ball with multiplier sigma 2MA and sigma M DC. This is smaller than S of B times 1/2, and this is smaller than S of B. So this one here is smaller than the sum of these two, right? And so this is the sum up to here, and for the sum up to here you do the same thing. I mean, sum up to here is the same as the sum from here to here, and this is an identical argument, and tells you that sigma MC is smaller than or equal to that quantity. Okay, but I know from this condition that sigma M is larger than S of B for some M. So what I get is that sigma of B is
1/2.
smaller than 1/2. S of D is smaller than half S of D plus SSB, which is exactly what I wanted to do. Right? So this is, I jumped over some further computations, but I hope you can understand what's happening. You can construct a new ordering which gives you what you want. That's it, that's all for today.
Thank you.